Okay, we're continuing with Chapter 3 in the chemistry textbook. In this video, we're going to go through Section 3.7, which talks about chemical reactions and chemical equations. So what is a chemical reaction? What is a chemical equation? And furthermore, how do you balance chemical equations? Okay. Having discussed the masses of atoms and molecules, we turn next to what happens to atoms and molecules in a chemical reaction, which is a process in which a substance or substances is changed into one or more new substances. To communicate with one another about chemical reactions, chemists have devised a standard way to represent them using chemical equations. A chemical equation uses chemical symbols to show what happens during a chemical reaction. In this section, we will learn how to write chemical equations and balance them. Okay, so far in this chapter, we've learned about the masses of atoms and molecules. And now for the remainder of this chapter, we want to talk about chemical reactions and chemical equations, as well as the mass relationships in chemical reactions and chemical equations. All right, and so a chemical reaction is a process in which a substance or substances is changed into one or more new substances. So like a combustion reaction, for example. You start off with a hydrocarbon and oxygen. The chemical reaction takes place, and you're left with, in general, carbon dioxide and H2O, but to where in the process, a lot of energy is given off. Now, in this chapter, we're not going to be talking about the energy relationships in chemical reactions. We'll do that in a later chapter. What we're talking about here in this chapter is, so that's a chemical reaction. That was an example of a chemical reaction where you have a starting substance or substances, goes through a chemical reaction process and converts to a ending substance or substances. That's a chemical reaction. But now, to communicate with one another about chemical reactions, chemists have devised standard ways to represent chemical reactions using chemical equations. So a chemical equation uses chemical symbols to show what happens during a chemical reaction. That's what a chemical equation is. It's a descriptive standard representation of a chemical reaction. Okay, and in this section, we're going to learn how to write chemical equations as well as balance them. So balance them, what does that mean? Well, with any chemical reaction, which is represented by a chemical equation, the whole system needs to obey the law of conservation of mass as well as the law of conservation of energy. The process of balancing the chemical equation is ensuring that the law of conservation of mass is obeyed. The law of conservation of energy, again, we're going to talk about in a later chapter. So, okay, but before we talk about balancing chemical equations, we're going to start with writing chemical equations. So consider what happens when hydrogen gas, H2, burns in air, which contains oxygen. So a combustion process, most commonly we think of as a fuel, like a hydrocarbon or hydrogen gas reacting with oxygen. Okay, but that's not a 100% requirement for a combustion process, that it has to involve oxygen and then some kind of hydrocarbon. Okay, but most typically what we do think of is the oxygen being the agent of the combustion process, and then combusting some fuel like a hydrocarbon, or just in this case, hydrogen gas. So hydrogen gas burns in air which contains O2 to form water. We typically think of a combustion process as the resulting products are carbon dioxide and water, but that's only the case if you're burning a hydrocarbon, right? You can't get CO2 out of a combustion process if you don't have any carbon in what's being combusted. All right, so this reaction can be represented by the chemical equation. So, okay, what's the reaction here? What's the chemical reaction? Again, a chemical reaction is a process in which a substance or substances is changed into one or more new substances. So the reaction is we have hydrogen gas in air interacting with oxygen gas. They interact and come together and transform into a new substance, H2O. That's the chemical reaction. A chemical reaction is just any chemical process that you could describe where you're starting with one or more chemical substances and then they interact and typically energy is given off or absorbed, and those initial substances are transformed into a new substance or substances. That's a chemical reaction. Now, to communicate a chemical reaction clearly for ourselves and between fellow students or colleagues, we represent chemical reactions with chemical equations. So we would represent this chemical reaction. You have hydrogen gas interacting with oxygen gas to form water. So what they do is they say, okay, H2 and then O2 on this side, and they put a plus to indicate that you have these two separate substances interacting. And then you put that these two interact and transform. They put an arrow, and you get H2O. That's the chemical equation corresponding to this chemical reaction. So it says where the plus sign means reacts with, and the arrow means to yield. Okay, so a plus sign means reacts with. These two substances are reacting with each other, and this means to yield. This is like the transform process. Okay, thus this symbolic expression can be read: molecular hydrogen reacts with molecular oxygen to yield water. The reaction is assumed to proceed from left to right as the arrow indicates. Equation 3.2 is not complete, however, so that chemical equation we just saw is not complete because there are twice as many oxygen atoms on the left side of the arrow, 2, as on the right side, 1. To conform with the law of conservation of mass, there must be the same number of each type of atom on both sides of the arrow. That is, we must have as many atoms after the reaction ends as we did before it started. Okay, so if we come here, what they're saying is this is incomplete because, so there's 2 oxygen atoms here on the left side, and there's only 1 oxygen atom here on the right side. And we could have figured out even before reading further that this was incomplete because this is we at the beginning of chapter 2 we learned about some of the fundamental laws of atomic theory, Dalton's laws. One of these laws being that a chemical reaction involves only the separation, combination, or rearrangement of atoms. It doesn't result in the creation or destruction of atoms. And so what that law is saying is that, yeah, you can have substances interact with each other and transform into some brand new substance, but all that's happening is atoms are getting rearranged. They're moving to other substances and being rearranged or just moved to other substances. But atoms are not being created or destroyed or like disappearing. Well, here, this indicates that an oxygen atom disappeared, right? And really, more precisely, the way you interpret Dalton's law is that the law of conservation of mass needs to be obeyed. That's the technical way to view this property that must be obeyed of any chemical reaction. And so to conform with the law of conservation of mass, all we do is we state that any chemical equation needs to be balanced. For it to be a correct chemical equation, it needs to be balanced in all circumstances. So you balance a chemical equation by placing the appropriate coefficient or coefficients in front of substances to where, so if you put a 2 in front of H2 and a 2 in front of H2O, now it balances. Why does it balance? Because, okay, you've got 4 hydrogen atoms on the left, 4 hydrogen atoms on the right, 2 oxygen atoms on the left, and 2 on the right. Now it's balanced. Okay? So is this fully complete? Is this a complete chemical equation? Okay, so it says this balanced chemical equation shows that two hydrogen molecules can combine or react with one oxygen molecule to form two water molecules. So, yeah, if we come here, we'll get a visual picture of this. This just shows the whole rearrangement process. So you have two H2 molecules and a single O2 molecule react with each other to form two H2O molecules, right? So for the actual reaction, you're having moles of molecules reacting with one another. It's not just like two H2s and a single O2 and two H2Os, right? It's hundreds of trillions of molecules interacting all at once. But this is just how you view the balanced reaction. You can't view it one H2 molecule at a time, because then if you just view it one H2 molecule at a time, it's not going to balance. The most simplified fundamental way to view this chemical reaction of hydrogen and oxygen combusting to form H2O is you say, okay, look, there's two H2 molecules and a single O2 molecule, and you get, it's like one of the oxygen molecules goes to two of the H's and another oxygen molecule goes to two of the H's, and you get two H2Os. That's it. Now, they write this here so here's the balanced chemical equation, but then you can also look at this as 2 moles of H2 instead of just two H2 molecules, because a mole is you're just scaling it up, right? Instead of 2 molecules of H2, you just multiply it by a mole. You multiply 2 by Avogadro's number, right? So then you could it's like you could multiply this entire chemical equation by a mole. You could say a mole of, or 2 moles of H2 atoms and a mole of O2, or 2 moles of H2 molecules and a mole of O2 molecules is going to result in 2 moles of H2O molecules. You just scaled everything up is all you did. You said, take this and multiply by Avogadro's number. Take this, multiply by Avogadro's number. Take this, multiply by Avogadro's number. Okay, but why would you do that? Well, you would do that because now you can convert with Avogadro's number and molar mass, you can convert from moles to grams easily, right? Using the molecular mass of H2, you can convert this to grams. And you can do the same thing here and the same thing here. And so now you can read this off in terms of grams. You can say 4.04 grams of H2 reacts with 32 grams of O2 to create 36.04 grams of H2O. Okay, because the ratio of the number of molecules is equal to the ratio of the number of moles, the equation can also be read as 2 moles of hydrogen molecules react with 1 mole of oxygen molecules to produce 2 moles of water molecules. Absolutely. Again, you're just scaling it up. You're just multiplying the entire equation by a constant. I could just as easily have looked at this and said, okay, here's the most simplified version of this reaction, but I could have said, okay, 8 molecules of H2. So if I have eight of these pairs, well, they're going to react with 4 molecules of O2 to create 8 molecules of H2O. It's the same thing. I'm just scaling it up. Well, okay, instead of multiplying each of these by 4, I multiply by Avogadro's number, and I put it in terms of moles, right? Remember, a mole is like the same idea as a dozen. A dozen H2 molecules react with half a dozen O2 molecules to produce a dozen water molecules. That's completely valid. But if I put it in terms of moles, well, then I can use the whole molar mass relationship to get it in terms of grams. Okay, we know the mass of a mole of each of these substances, so we can also interpret exactly. With moles, now we can use molar mass to convert to grams. So now you could say 4.04 grams of H2 react with 32 grams of O2 to give 36.04 grams of H2O. These 3 ways of reading the equation are summarized in the figure. We just looked at that. We refer to H2 and O2 in equation 3.2 as reactants, which are the starting materials in a chemical reaction. Water is the product, which is the substance formed as a result of a chemical reaction. So in any chemical reaction, the starting substance or substances are called the reactants, and the The finishing substance or substances are called the products. A chemical equation, then, is just the chemist's shorthand description of a reaction. In a chemical equation, the reactants are conventionally written on the left and the products on the right of the arrow. Yeah, so if you wanted to, it's really technically the reactants are on the side of the arrow away from the arrowhead, and the products are on the side of the arrow near the arrowhead, right? So you could do it if you wanted to. You could say products, reactants. It's really more about the where the arrow is pointing, but we read from left to right, so it's typically just done this way. Now, okay, to provide additional information, chemists often indicate the physical states of the reactants and products by using the letters G, L, and S to denote gas, liquid, and solid, respectively. Okay, so this equation, once you write all of the reactants and all of the products that are involved in the chemical reaction on each side of the arrow, you're not done yet. It needs to be balanced. So then once you balance it, then that's technically all you need to have a chemical equation. You show all of the substances that are reacting with each other, and then you show all of the products that are not really reacting with each other, but you'd still put a plus just to indicate all of the what's come out of the reaction that are involved. You can't not show certain substances that are involved, or else that wouldn't be a complete chemical equation. Okay, but if you show all the reactants and products involved, then it needs to be balanced. If it's not balanced, it's not complete. But once it's balanced, then you have a complete chemical reaction or chemical equation representing a chemical reaction. Okay, but you do have the option, if you want to make your chemical equation more descriptive, you have the option of indicating the physical states of the reactants and products. So indicating, do you have is this substance a solid, liquid, or a gas? So here, this chemical equation is saying that two molecules or moles, you can't say like grams because the coefficients are only going to be in terms of the individual molecules, or the same thing would be moles, right? So two, let's say, molecules of carbon monoxide gas react with a single molecule of O2 gas to produce two molecules of CO2 gas, right? So you can indicate the states here. This would be an ionic compound, so just two units of mercury oxide solid. And here they're not reacting with anything, they just decompose in some process to produce two mercury atoms in the liquid state and a single O2 molecule in the gas state. Okay, to represent what happens when sodium chloride is added to water, we write, so okay, solid sodium chloride, when it interacts with water, becomes sodium chloride aqueous. So aqueous is another state that we're going to talk about in the next chapter. It's not a state of matter like solid, liquid, or gas, but you'll see exactly what aqueous means in the next chapter. It means dissolved in water. So where aqueous denotes the aqueous, that is water environment. Writing H2O above the arrow symbolizes the physical process of dissolving a substance in water, although it is sometimes left out for simplicity. So yeah, they're talking about this here. Putting the H2O above the arrow is just letting you know that you're dissolving the reactant in water. But a lot of times you don't have to put this. A lot of times it's just left out for simplicity. Knowing the states of the reactants and products is especially useful in the laboratory. For example, when potassium bromide and silver nitrate react in an aqueous environment, a solid silver bromide is formed. This reaction can be represented by the equation. So potassium bromide aqueous plus silver nitrate aqueous gives potassium nitrate aqueous plus silver bromide solid. Yeah, so we're going to learn that there's some chemical equations where you really do need to indicate the states of the reactants in products because it's part of the nature of the reaction. So this is we're going to learn in the next chapter, this is a precipitation reaction. And without the indicating the states, you don't know what's a precipitate and what's not. So really, I would say a general rule is if it's possible, go ahead for any chemical equation, show the states of the reactants and products. Why not? But it's not a requirement, but I would say in general, why not indicate the states? In particular, when you think about when we talk about the energy relationships in chemical reactions, that's another circumstance where you need to know states, because if a product is, let's say, H2O gas or H2O liquid, well, that's going to be a function of how much energy was given off in the reaction or absorbed, right? You're going to give off less energy if you're dealing with a H2O gas versus a condensed H2O liquid. Okay, if the physical states of reactants and products are not given, an uninformed person might try to bring about the reaction by mixing solid potassium bromide with solid silver nitrate. These solids would react very slowly or not at all. Imagining the process on the microscopic level, we can understand that for a product like silver bromide to form, the silver cation and bromide anion ions would have to come in contact with each other. However, these ions are locked in place and they're solid compounds and have little mobility. Here's an example of how we explain a phenomenon by thinking about what happens at the molecular level, as discussed in section 1.2. Yeah, so again, it's a good rule of thumb to, if at all possible, put the states of the reactants and products. Because when you do that, you can get a sense for, well, first of all, if someone wants to recreate the reaction in a lab environment, this will give the chemist much more direction on what needs to be done, on what's happening. But I mean, if you're just studying chemistry and you're trying to imagine a chemical reaction, then you want to know what the states are. Is this a gas reacting with a liquid? Two gases reacting together, right? What they're talking about here is a precipitation reaction is intimately related to having these ions dissolved in solution. So you need to know that you're dealing with an ionic compound dissolved in water. An ionic compound dissolved in water is different from an ionic compound just on its own as a solid. What they're trying to say here is if you just took potassium bromide solid, ionic compound, and silver nitrate solid and just mixed them together, you're not going to get a silver bromide solid. No, you need these dissolved in water as ions, which we're going to talk about more in the next chapter. Then these ions all mix together and interact, and what precipitates out is a silver bromide solid. So it's saying, like we talked about in section 1, it's in chemistry, you explain phenomena, chemical reactions, by thinking about what's happening at the molecular level. And you can think about what's happening at the molecular level if you know the states of the reactants and products. If you know the states of well, I guess in particular the reactants, that's where the reaction's happening, you can visualize what's going on. If you understand the chemical structure and properties of solids, liquids, and gases, and or a substance dissolved in water, then you can look at the reactants and look at the states and sort of think about, okay, this is how the reaction, how all the molecules or atoms are interacting to produce the products and the states and whatever states the products are in. Okay, now balancing chemical equations. Suppose we want to write an equation to describe a chemical reaction that we have just carried out in the laboratory. How should we go about doing it? Because we know the identities of the reactants, we can write their chemical formulas. The identities of products are more difficult to establish. For simple reactions, it is often possible to guess the products. For more complicated reactions involving 3 or more products, chemists may need to perform further tests to establish the presence of specific compounds. Once we have identified all the reactants and products and have written the correct formulas for them, we assemble them in the conventional sequence. Reactants on the left separated by an arrow from products on the right. The equation written at this point is likely to be unbalanced. That is, the number of each type of atom on one side of the arrow differs from the number on the other side. In general, we can balance a chemical equation by the following steps. So, yeah, in general chemistry, introductory chemistry, we're most familiar with when it comes to balancing chemical equations, we're just given the unbalanced chemical equation to start, where you have all of the reactants on the left side of the arrow, all the products on the right side, but there's no coefficients, and you have to apply the appropriate coefficients to balance it. But here, this is pretty interesting. They're giving us a more realistic sense of when chemical equations need to be balanced. So in a laboratory setting, for example, you might be carrying out a reaction. Well, in general, you're going to know what the reactants are, right? So you'll write out the chemical formulas of the reactants. Then you'll put an arrow, but you don't put any coefficients in front of the reactants to start with. Then you need to write out what the products are, and maybe if it's a simple overall chemical reaction, you can guess what the products are, because the chemical reaction is going to have to obey the law of conservation of mass. So the products are going to have to be some combination of the atoms of the reactants, right? So maybe you could guess the products, but if it's a more complicated overall chemical reaction, you might have to do an experimental analysis to see what products are present. Even if there's some products that are present in a smaller amount than other products, still, you would list the chemical formulas of all of the whatever has come out of that reaction. And then once you've accounted for all reactants involved and all products involved in the overall chemical reaction, then you have this raw chemical reaction here with no coefficients applied. Then you go through the process of balancing the chemical equation. So this is pretty interesting. It just gives us a sense for whenever you're practicing balancing chemical equations, you have a sense for where that equation comes from, where a raw, unbalanced chemical equation might come from. So, okay, once you've got the unbalanced chemical equation, what's a general approach you can use to balancing it? What are some of the tricks, techniques that you can use for balancing a chemical equation? So, okay, step one, identify all reactants and products and write their correct formulas on the left side and right side of the equation respectively. That's what we just talked about. Okay, step two, begin balancing the equation by trying different coefficients to make the number of atoms of each element the same on both sides of the equation. We can change the coefficients, the numbers preceding the formulas, but not the subscripts, the numbers within formulas. Right, of course. You can't change, if you have H2O, you can change the coefficient, but you can't change any of the subscripts, or you're going to change the substance. Changing the subscripts would change the identity of the substance. For example, 2NO2 means 2 molecules of nitrogen dioxide, but if we double the subscripts, we have N2O4, which is the formula of dinitrogen tetroxide, a completely different compound, of course. Okay, first look for elements that appear only once on each side of the equation with the same number of atoms on each side. The formulas containing these elements must have the same coefficient. Therefore, there is no need to adjust the coefficients of these elements at this point. Next, look for elements that appear only once on each side of the equation but in unequal numbers of atoms. Balance these elements. Finally, balance elements that appear in 2 or more formulas on the same side of the equation. Yeah, so for tip 3 here, I would group all of this into one statement. So what you want to do is you can start off by, actually, I'm going to make a separate video on this, going through the steps that I would say you should take for balancing any chemical equation, because I would use step 4 first. It says, check your balanced equation to make sure you have the same number. Okay, well, they don't even, step 4 is just saying whenever you're done balancing, go through a check to make sure that the atoms are balanced. So they don't even mention some of the tips that I'm going to talk about in the next video. There's a dedicated video on balancing chemical equations. The first thing I would do is, with any chemical equation, I mean, most people are just going to go through the whole trial and error process, which they talked about at the beginning of step 2 here, where you're just trying different coefficients, plugging in coefficients, erasing coefficients, putting new coefficients until you get it balanced. And for relatively simple chemical equations, that's going to work fine. But if you're trying to have a general process for balancing any chemical equation, like even the really complex ones, then the first thing I would look for is lone elemental forms of substances. So like if we come here we have an elemental form of oxygen, oxygen by itself. You might have more than one of these. You might have an N2 or something as well. And you want to look for those first. And if you see an elemental form, then you want to balance the entire chemical equation, ignoring like the oxygen in this case first. Balance, just act like oxygen doesn't exist and balance all of the other elements. If there was an N2 here or something else by itself, then ignore that as well and balance all the other elements. Because once all the other elements are balanced, then you're pretty much done, because then you can say, okay, now let's come and balance the oxygens, and then maybe if there's a nitrogen or something, you could just balance that with no problem, because this is by itself. You have full control over the count here. What makes balancing chemical equations difficult, if it's a complicated one, is that you're going to have these substances with all kinds of different elements mixed in. So when you change the coefficient, you're changing the numbers on all those different elements at the same time. Here you've got full control. You can, whatever is unbalanced about the oxygen, you just put it here, and you're not changing anything about another element. So that's why if you got these lone elemental forms of substances and you balance everything else, then you're pretty much done, because you can just go to these elemental forms and put whatever coefficient you need. And that brings up another technique you want to use, because you might be thinking to yourself, well, what if it's like not an integer number? Like what if the amount of oxygens you need, the coefficient you need to apply here is not an integer? So maybe you've got like here, if we go to balance this, we could say there's one potassium on both sides, there's one chlorine on both sides. Okay, so the potassiums and chlorines are balanced. Now let's balance the oxygens like I just talked about. So you have 3 oxygens on the left and 2 on the right. So, okay, so what coefficient do we put? Well, we would put 3/2, because 3/2 times 2 is 3. Now we have 3 oxygens on the left and 3 on the right. And now you're saying, well, wait a minute. Well, you can't have a fractional coefficient. That's true, but this is still balanced, right? If we multiply an entire chemical equation by a constant, then it's not going to change any of the numbers. So we multiply this entire equation by 2, and you get a 2 here, a 2 here, and a 3 here. Now it's balanced. You see? So the second tip is that if you're able to balance a chemical equation with a fractional coefficient, if you can see clearly, if I add a fractional coefficient, one or more fractional coefficients into the equation, it's going to balance. Do it right away, because if it's balanced, then to get rid of the fractions, you just multiply through by the least common denominator. Okay, so you want to look for the elemental forms. You start by looking for elemental forms of atoms, then ignore those, balance everything else, then you're done, because you could just put whatever coefficients you need, fractional coefficients, in front of the elemental forms, multiply through by the least common denominator, and you got it. Okay, now the third step that I would go to is what they were talking about in step 3, and what they're saying there is you want to look on both sides of the chemical equation for any elements that are just in one substance on the left side and one substance on the right side. Okay, so I'll say that again. You look at all of the products on the left side. if you see a certain element, it doesn't matter what the subscript is. Just there's an iron element just in one of those substances for all of the substances on the left side, and then there's the iron atom is on the right side just in one substance of all of the substances of the reactants. It doesn't matter what the subscripts are. Well, you want to take advantage of the fact that the coefficients on those substances, you're going to be able to establish a relation between them automatically. So, okay, let's see. They balance, so the 2KL, KClO3, 2KCl3O2, okay. And then they just check it's good practice to, once you've done balancing and you think you're done, check the final answer. So 2 potassiums on the left, 2 on the right, 2 chlorines on the left, 2 on the right, 6 oxygens on the left, 6 on the right. So it's balanced. And then they're noting here that, if you multiply the entire equation by a constant, you're not going to change the balance. So even here, you've multiplied through the balanced equation by 2. This is still balanced, but this is similar to the fractional coefficient in that it's still, even though it's balanced, it's not technically correct because you want to have the smallest possible whole number coefficients. Here you can divide through by 2. So, all right, let's see. So, okay, this chemical equation, you've got the oxygen by itself, so we could ignore the oxygen, but let's focus on the lone elemental forms. So, okay, the idea is, and again, this is a relatively simple chemical equation. You could just do this by trial and error, but let's practice these techniques. So you see you've got a carbon in just one substance for the entire left side. Carbon is just in one substance, and also same thing on the right side. What that means is that these coefficients are going to be related. They have to be. Like this here, if let's see, this is x, then this is going to have to be 2x. This coefficient is going to have to be twice this coefficient. We don't know what the coefficient is. We don't know what x is, but for sure this coefficient is going to have to be twice this coefficient, or else the carbons won't balance. So you can take advantage of that. What you do is you put like an x here and a 2x here. Okay, now we could do the same thing with the hydrogen, since hydrogen's by itself here and just in one substance here and in one substance here. So there's 6x hydrogens on the left, so there's going to have to be 3x. This is going to have to be 3x coefficient to make 6x hydrogens on the right. Okay, now let's see. We've got, how many oxygens in terms of x do we have? You've got 4x plus 3x oxygens. So 7x oxygens on the right. So there needs to be 7x oxygens on the left. So we can say 7/2 x. All right, now if we multiply through by 2, we get 2x, 7x, 4x, 6x. 2x, 7x, 4x, 6x. And so now we're done. You might say, well, what about the x's? The x, we can make whatever we want. The whole idea was we just know that this coefficient needs to be twice this coefficient. This coefficient needs to be 3 times this coefficient. So what are we going to make the x? We'll just make x equal to 1 because it's going to need to be the smallest possible whole numbers, right? So 2, 7, 4, 6. That's it. You see how we took advantage of the fact that with these lone elements, an element by itself in one substance over here, and that same element by itself in just a single substance on the right side, that constrains what the coefficients must be to balance that lone element. You see how we took advantage of that? Okay, so they go through the whole process, then they check their final answer. All right, so let's see. Let's look at this example. We've got let's balance this. Here they give the whole backstory, which is, you can read that. That's interesting, on where the chemical equation comes from, the unbalanced chemical equation comes from. But look, I mean, we've got these lone elemental forms here. It's going to be easy. So to balance the the aluminums, you got 2 here. Now the aluminums are balanced. Now to balance the oxygens, we've got 2 on the left, 3 on the right. So now it's balanced. But we want to multiply through by 2, so it's going to be 4, 3, 2. And there you go.